Okay, so last day we looked at a whole bunch of non-Cartesian ways of doing, looking at some high-dimensional data, uh, ending, largely with glyphs to begin with, thinking about those Nightingale glyphs and then star glyphs. And star glyphs are a special case of radial axes as opposed to orthogonal axes. And then parallel axes, point line duality, how to interpret that, those sort of things. And again, using Eulerians, all that graph theory for ordering axes on the radial axes or the parallel, any serial ordering of the axes. And then a couple of analyses. Looked at the minorities data last time. And I again encourage you to go and play with that stuff yourself. And we finally ended with looking at those high-dimensional glyphs, which are based on space-filling curves and heat maps. Any questions on anything that we've done on that stuff? Okay. So nope, there being no question, at least none that anybody's willing to air. Let's look at something that should be more familiar to you. Going back to your linear algebra or your regression course, wherever you've seen this stuff, and that is projections. Because we're still talking about axes, axis is a particular one-dimensional ray through the space, so one-dimensional subspace. When we look at points on that axis, that's a one-dimensional projection. In fact, everything we've been doing so far, like even the zero-dimensional single dot somewhere with the zero-dimensional data, and then one-dimensional data, you think of it as projection onto a one-dimensional subspace. A scatter plot 2D data, projections onto the two-dimensional subspace. 3D data, projections into a three-dimensional subspace. Every time we look at marking anything on an axis, we're looking at the projection of that, the data onto that particular one-dimensional subspace. So I want to remind you of some stuff from LinAlg. And if you think about vector spaces, and vector spaces being in real space here. So we've got some d-dimensional real space and a collection of important being k linearly independent vectors with k less than d. That set is a basis. So these are non-zero vectors. So we've got a set of k linearly independent non-zero vectors. You would think about all linear combinations of those. That itself is a subspace, right? A k-dimensional subspace of the real D space. All remember this? Great. You okay? Yep, k can also be equal to d. What it can't be is bigger than d in this case. But yeah. It's just if you think about it, for when we've had high dimensional data, if d could be 1,000 and we only look at a scatter plot, suddenly k is 2. So we're often looking at a k that's smaller than the d dimensions. So that set of all linear combinations of those k vectors is a subspace. We sometimes call that set of all linear combinations the span of that set of vectors. The k vectors form a basis for that subspace. And now think about a matrix that is d by d, that has the following properties, that it's idempotent, in that p times p is p itself again. So it just brings it back to itself. And think of applying that to any arbitrary vector, y. So if P, that matrix P has that property, it's going to be a projection matrix. So P times y, the vector y, is going to return another vector. That vector is still within the d-dimensional space. But in fact, by the virtue of its construction, P times y is clearly a linear combination of the column vectors of P. just because that's how matrix multiplication works, right? Matrix vector multiplication. If it's a linear combination, then the vector that results from multiplying p times y lives in the column space, the space of the span of the vectors, of the column vectors of p. Right? So p takes a vector y and pushes into whatever the column space is of the matrix P. And it does that, it's a projection. And the indication that it's a projection matrix is if I do it again, nothing happens. P times Py is the same as Py. And that's where that idempotency comes in. Okay? Make sense? If I just project me onto the floor, and I do it again, nothing happens. Right in there. So that's what idempotency is, and that's what makes it a projection matrix. Now, if it also happens to be symmetric, then it's an orthogonal projection matrix. Which, yes, I do mention it. Good. So we can talk about the column space of P and the column space of I minus P. If P is idempotent, so is I minus P. I think you did that in assignment 1 or 2. And so these things are orthogonal. If P is an orthogonal projection matrix, these are orthogonal subspaces. And they're complementary. Any questions? All familiar? Okay, good. So the next step is, if I have a space that I'm interested in, given by some set of vectors v1 to vk, and those vectors are linearly independent and non-zero, so that is the form of basis, that set, I can easily construct a projection matrix that will project any vector in Rd onto the span of those vectors v1 through vk. Namely, V transpose V inverse, V transpose. Okay? And that should look familiar. That should look like a regression projection operator if you've taken a course in regression and linear models. Is that familiar to everybody? So if that should be an orthonormal basis, yeah, P in fact looks kind of nice that it's just V times V transpose. That is, if V transpose V equals the identity matrix, the middle part disappears. So a classic mistake is that people think that P must be equal to the identity matrix because they take that V transpose V inverse and take the V inverse out and the V transpose inverse out. That can't happen. Why can that not happen? Anyone? Can that happen? What's the dimension of V as a matrix? How many rows, how many columns? K what? K rows and K columns? Nope. Close. Number of columns is easy. K. How many rows? D rows. And if K is less than D, that's not a square matrix. So I don't know how what you're talking about when you're saying you want the inverse of that. Okay, so that's not going to happen in general. Okay, so there are some peculiar ones, and you end up that if that was an orthonormal basis, then clearly the columns of P, there are still going to be D columns of P. P is still a D by D matrix. they must live in the span of the vectors v1 through vk. Why? Because every column of P, if you think of the first column, it's going to be, we've got a product of two matrices, it's going to be taken from the first column of this second matrix, right, times the matrix V, which is going to be a particular linear combination of V1, V2, up to Vk. So every vector, column vector in P is a linear combination of vectors in V, the column vectors in V. So they form a basis. That's true up here too, it's just this second matrix is a little more complicated. They form a basis for the column space of P. Okay? So I'm going to use the letter E to indicate an axis. So E sub I will be the ith axis. It'll have a 0 everywhere except a 1 in the ith position. And I could just use this as if it were a single vector. I'm interested in projecting onto the space spanned by EI. That is, it's a one-dimensional space. And that's going to follow the same rules as we had up here, replacing V by EI down here. EI transpose EI is 1, right? That's just that vector times its transpose. And we end up with that projection of the y onto that direction is, not surprisingly, that one coordinate, yi. So all of the math that you have here just reproduces what you would do when you say, I want to select one of the variates and look at that. Just reassure you that that is in fact a projection onto the ith axis. You're looking at the ith variate. Okay? So projection onto an axis, you think of that as selecting a particular variate, which is another way of ignoring all the rest. When we ignore all the rest, we think that in statistical terms and probabilistic terms, think about marginalizing. So we're looking at the marginal distribution of that one variate, or a sample from the marginal distribution of that one variate. Okay? So that should connect your lin-alg to the statistical part, to the data, to the visualization. You're just projecting things. Okay? Everybody okay with that? Yes? Start again, because I'm not catching you. Wrong. S is the span V1 to Vk. If S is the span of V1 to Vk, then how many dimensions? It's got to be k-dimensional. They happen to be vectors that are have D elements. Okay? The orthonormality's got nothing to do with it. It just simplifies things. Any set of k linearly independent non-zero vectors that span that space will do. In fact, that's all of the stuff that's underlying all the things you did in lin-alg when you were doing row reduction and all the rest of that. You were just finding different expressions for these various spaces. Okay, so back to Cartesian coordinates. So think about that iris data again. It's only got 4 dimensions. And with each of the measurements on the flowers, the width and length of the sepal or the width and length of the petal. And if I look at any one of these, so x, y, z, w, any scatter plot here is that 4-dimensional cloud projected onto the 2-dimensional subspace spanned by the corresponding axes, vectors, the unit vectors, okay? So every one of these is a plot onto a pair of axes. So you go back here, do the same thing, and take an EI and an EJ, put them together in a matrix. form, let that matrix, so V becomes EI, EJ, so it only K equals 2. Plug it in here, it'll look like this because they're an orthonormal basis. Apply it and you'll find that the vector you end up with is a vector with all zeros except an I, a value in the ith position and a value in the jth position. Okay? So that's how we're going to pick things off, is just by picking particular projection. So every one of these is just a different pair of values I and j. So to get some sense of what's going on in a higher dimension, we have to think about how are these three displays here, for example, connected. So there's an advantage here of looking at these three in that at least the first one and the third one, they have a common aligned scale, that y-axis, the vertical axis. The middle one, not so much. The middle one's not y. The middle one has a w on that vertical axis. So you're losing that. But these two, at least, become a little more comparable. You can kind of imagine where the points might be in 3 space. So in some sense, you can imagine that the points, say the points are in 3 space. We just think of x, y, and w here. Forget about z for the moment. And imagine they're inside a cube. So the points are sitting inside a 3D cube. I'm looking at one face here, the x, y face, and I just turn it around, and I'm looking now at the y, w face of the cube. So it's not hard to take this picture and that picture and kind of imagine what that 3D point cloud looks like. A little harder for these two, principally because although it's a common scale, they're not aligned. The W is mismatched here. So I have to do this translation from this vertical to this horizontal scale. The other thing that's helping me is just coloring these things, so it's easy to tell the Setosa group, the pink group, so it's easy for you to match those across displays. So all that stuff that we learned in the first week is in operation here, hopefully allowing you to construct what looks like a higher dimensional space. Now, unfortunately, we've got 4 dimensions. So when we try to look at all 3 of them at once, that becomes a bit more of a challenge to figure out what does that look like in higher dimensional space. So if you want to think about linking, how do I link information from one display, one set of projections to another projection? So serial axes link the dimensions just by that layout. You know, they're parallel, moving along, and I can follow that curve. So every point was a curve or a glyph in the 2-dimensional layout. And that allowed us to link points across the display. What I want to do is the same sort of thing to link points in the 2-dimensional display, but with Cartesian coordinates. And the way that's done is to think about looking at all pairs of scatter plots. So this is the pairs plot, and it's going to look at all pairs of scatter plots. I'm just going to look at the first 3 dimensions here. And what I'm going to note on the next, we'll come back to this, is to lay it out in this fashion. And the linking here is, again, if we look at this top row, the vertical is a common aligned axis. So this vertical axis in the top row is sepal length. So I can easily connect these two. In this last column, the axis that's connected is petal length. So these are common aligned. So I can connect these. These are the face of the cube, and I'm allowing the layout itself to give you some sense of the 3-dimensionality. Okay? So in every row, I have the same vertical axis. So this plot and this plot has the same vertical axis, but different horizontal axes. In every column, I have the same horizontal axis. So common aligned scales by column and by row. Everybody with me? So you can improve that slightly. If you think about, instead of having the diagonal go from, as we might in a matrix, go from the 1, 1 position down to the 3, 3 position, if we made the diagonal go in the other direction, something interesting happens. And the interesting thing that happens is, if you look at any pair plot across the diagonal, they're kind of mirrored images of one another. You imagine that there's a mirror across this diagonal, they're mirrored. And what's good about that? Well, that actually looks like the faces of a cube. If you had the 3D points inside a cube, that's what, and you looked around on all sides, that's what you would see. If you look at that one, which is the standard, it's not so easy. Now we'll go across the diagonal. This one and that one are the same scatter plot. But what's happened? I've kind of got this rotation happening here, don't I? I have to think about this one turning into that one. I have to turn it clockwise to get that red on the side. And the purple will be on the right-hand side then. But it's still not quite right, in that this red will be on the bottom up here. It needs to be flipped. It's a rather complicated transformation between these two. So some people will argue that this is just a more complicated plot, and by far the preferred thing is that, because it's much simpler. These are just mirror reflections. Much easier to connect. Okay? Great exam question. Any questions? Everybody see that? It looks like these are reflected. You're looking around the face of the cube. There's a more complicated transform to get from this plot to that because of inverted axes and rotated things. Yes? Yeah, we did that. So the question is there any way to draw a cube, a box? We did that using 3D graphics, right? And you can rotate that around in real time. And there you're connecting, it's important, you're connecting things with motion. So you've got this illusion of 3D, and you can look at either side. This is just layout in a static display. So I can make that connection. Yes? So you imagine a mirror here, right? That's up here. Where's the glass when you think that's a mirror? Here? Then this way? This way? Yes. Yeah, fair enough. So that is a flip in the bottom left corner about this axis. But that's what the other side of the box looks like. So if you were to fold that up into a box without doing anything more damage to it, that's what the faces would look like, the 6 faces. Not so for that. Okay. The other thing you can do is on the diagonal, this seems to be wasted, this space here. So you might put one-dimensional information on the diagonal. That's easily enough to accomplish. So with a panel function, so you see the, you see the diagonal panel here is the panel hist, which is this function that we've written here. What are we going to produce there? And it's going to be a histogram of sorts. So I'm just doing some tidying up so it looks kind of nice. So I can produce that. And now I've packed a lot of information into the pairs plot. I've got the 2D plots, 2D projections, and some measure of the 1D projection there just being histograms. So you can see the marginal distributions of that variate lined up here. Okay. So again, taking advantage of the space that's available, rather than just have it represent a label of what the variate is, let's have some information there. So that's giving you some sense, I guess, of connecting 1D projections, and again using a histogram, and 2D projections, here using scatterplot. What's cool about this, which doesn't work for RGL, is there's nothing special about 3 dimensions. So we can look at all 4 dimensions in a pairs plot. And all we're doing is any row has a common vertical axis. Any column has a common horizontal axis. So we won't get that with rotation, right, in 3D, because it's actually a 4-dimensional cube. Okay? So looking at all 4 dimensions at once, that is all pairs of variates, we get some sense of the 4-dimensional structure. Although granted, that's a little harder to conceive in 4 dimensions, but we can think about looking at any 3-dimensional subset, any 2-dimensional subset, any 1-dimensional subset. Okay? Any questions? All right. You can do this in 8 dimensions, any number of dimensions, and it gets a little more interesting if you've got some linking here. So let's see if I can, what am I looking for in 8 dimensions? So hopefully this works. Oh, sorry, this is just the pairs plot itself. I'm getting ahead of myself. That's not going to be activated. So that's the pairs plot itself, which looks like that. It's 8-dimensional data. So that's just getting the data set from Loon. So there's the olive data in all of its 8 dimensions. You see that there's some structure in some projections and a little less structure in other projections. You know, some have got some nice monotonic relationships between variates. Others have some groups separating into a couple of groups, and then others have a lot of other little artifacts that are kind of interesting in the data set. But you're getting to see the whole 8-dimensional space at once. And how are you seeing that? You're seeing that through a bunch of 2-dimensional projections. Okay, so it's great that you can go to large numbers of projections. And here's where I am, right. So the next guy. In Loon, same sort of thing. Now becomes a little more interesting if you can make that interactive. So in Loon, it's an L underscore pairs as opposed to a pairs plot. And you can have a lot of things. So we've got now a serial axis, parallel axis plot. I'm just going to make this a little bit smaller. Again, a reason to have a big screen. And the pairs. Now, in Loon, the pairs plot, it's not doubling all of those plots. Every plot is only appearing once. But now we start to look at, as we did before with the olive data, looking at this group here and seeing what group that corresponds to. In fact, that's a group that's entirely separated here, right? Which again, I might cut that away, or I might have that one kept, invert, and deactivate the rest. And again, you start using this pairs plot, and you're seeing a little more structure in some of these two-dimensional scatter plots that are perhaps a little hard to tell here. So where's that? And that seems to be picking off this group, this one group that's separating in a few of these scatter plots. And let's see what this group here is. Put the next one down. There we go, the next one. And what we're seeing here are these lines, right? That should reassure you about the parallel coordinates. I mean, that's a single line in this space and a bunch of lines over there. So those are kind of interesting groups themselves. So you combine this with a non-Cartesian serial axis, pairs plots, and linking, and you can get a lot of information about the higher dimensional structure. Any questions? Okay. So that's just, sorry, yes? So it's all, what sort of conclusions? It depends on the purpose of the analysis, right? So the way I presented it, it's kind of exploratory, and I'm looking to see are there groups. So that would be a case that you didn't know what the areas were, and you're looking at all of these different fatty acids and seeing whether you can distinguish. Just noticing those patterns. You want to know why those patterns are there. So that's just an exploratory sense. If I was actually thinking of a classification, right, that I want to have some rules for how would I detect what region the olive oil came from, then everything that I do here, you see that? That's a simple rule. And it's based entirely on, I can turn that into mathematics into an SQL query if I wanted to, that's, you know, on this variate, if it's less than this amount, it separates into these two groups. The other one's above. And then as I brush, every brush is a rectangle, so that's bounds on two sides. I can, as I grab these guys, you know, that's again, you can turn that into a mathematical expression. So you could build a classifier based on this interaction if you're capturing it. In fact, there's some great software by Al Inselberg on parallel coordinates where he does just that with building classifiers and turning them into SQL queries from the parallel coordinate axes alone. No, that's not true. Parallel coordinates axes and a scatter plot you can look at. So these, every brush here is a mathematical construct, so it becomes a rule. It's just one visually determined. And certainly in various competitions, he's been competitive with some automated methods and has outperformed in some cases. So I'm not sure if that answers your question. It depends on the problem, what you're doing. If we were doing, you know, trying to find relationships between these variates, it would be a slightly different thing that we would be looking at. You'd be more interested in the correlations and maybe some other measures. But this is classically clustering or classification. So it looks, you've seen L underscore serial axes. The only thing I've added here is this L pairs, and that they're shared in the same linking group. So another way of doing this is by linking things in time. We saw that when we did 3D rotation. It's effectively linking those points because they're not far from each other in any between any two time points, so you can kind of track one into the other. So remember when we did 3D rotation, we looked at a scatter plot, which was effectively a plane. Project all the data onto the plane, and then move that plane and show you the projections of the data on every plane in between the beginning and the end plane. And that looked like a 3D rotation. So what's happening is you've got a 2D projection, 2D, 2D, 2D as I'm moving that plane around. The illusion is that we're actually looking at a 3D projection, a 3D subspace. So we did that remember we made that explicit in Loon, where we're actually just rotating around one of the axes at a time, not arbitrary directions as you would with RGL, but around particular axes. So as we're moving on this navigation graph from one pair of variates to another pair of variates, we're doing a rigid rotation between these. So these go from SBP IDL to SBP tab. This is looks like the South African heart disease data, tobacco and lipid levels and systolic blood pressure. We're doing a rotation, rotating this IDL axis into the TOB axis, the tobacco axis. Okay. And so we've seen that. That's how we do a rotation around one axis after another. And the question is, could we make that more general? And why not? Right? So if we look at all pairs, in this case, we're looking again at the iris data. So for our four-dimensional data, every pair of variates appears as a node, and a line, an edge appears between them if they share a variable. So there's no line between these two nodes because there's no variable in common. But along here, so along each edge should be some kind of rotation from one 2D plane into another. Okay? So I want you to think about that. This is a four-dimensional space that has a bunch of two-dimensional subspaces sitting around on the nodes, where we could look at a picture of that. And as we traverse along an edge, we're moving through a three-dimensional transition. 3D transition from one 2D space to another 2D space. And I could just travel around this whole graph. Okay? So that's why we call it a navigation graph. I can just travel this around. I've gone from, in this 3D space of sepal length, petal length, and sepal width, up to there, and now I'm in a different 3D space. This 3D space is sepal length, and petal width, right? So smoothly transfer from one 3D space to another. Okay? So let's have a look. So there's this L underscore nav graph. We're looking at all of the different coordinates at once. So we can still play the same game that you've got the parallel coordinates laid out. Here we have every pairs appearing. We have a 2D scatter plot. I'm going to make this again smaller. We have a 2D scatter plot that's showing two-dimensional projection. So again, this is Setosa down here on the parallel axes, and you see where it appears up here. There's that oddball here, which looks odd here, and it appears there. And over here is the navigation graph, and the navigation graph is showing you all pairs of variates. And so the current scatter plot is sepal length and sepal width. You see here, and as I shift select, I can see where I can go to, and I can start to get a whole trajectory through this four-dimensional space. So as I move along this trajectory of getting that 3D rotation as we had before, in the space of sepal length, sepal width, and petal length, you see that on this axis, it's a linear combination of two of those. And as I continue on, I'm suddenly in a different space. So what I'm going to do is I'm going to move through this four-dimensional space through a whole bunch of 3D transitions. So kind of got this wormhole that I'm moving through the 4-dimensional space through a bunch of 3-dimensional subspaces. Okay? I'm doing that entirely by pushing a single plane around. So I'm taking one 2-dimensional projection and moving it around through the space from one axis to another, and there's a fourth axis here which I can't represent. But a 2D space can move, a 2D subspace can move around anywhere in the 4-dimensional space. It's just moving on that, as long as it's going through the origin. So it gives us a way to navigate through this high-dimensional space. So backwards and forwards and seeing what's there. So in some subspaces you may see something interesting, right? And mark that in some way. And then continue on our merry way to see where that is, whether that stays the same. So you've got the spatial connection in temporal use. So the sequence is entirely temporal. That is, it's changing in time. And let me just make this a little smaller. But we're able to connect them, which dots are which, just following them. Okay? Any question of what's happening there? So using time. Okay. Does that make sense? So that should be very reassuring because that looks, whoops, wrong one. That looks like our regular life, right? You're just moving around 3D space, everything's a nice rigid rotation. Well, what about these axes? Sorry, not these axes, these edges. The edges that are missing. They're missing because there's no varied in common. That's this graph. Oops. Okay. All right, bug. I apologize because I'm not working with the Loon you have. I'm working with the beta version. So let's see if we can get through this. There we go. So far so good. Whoa. This is one of the missing edges. No longer a rigid rotation. Let's carry on. So I can start moving around through this whole space. And suddenly things, that's not a rigid rotation. These look more like black flies, right? They're just bugs moving around. What's happening? Well, along this edge, we're starting with some 2-dimensional projection, and we're ending with another 2-dimensional projection. So 2 sets of vectors, those E1 and E2, let's say, and we're going to E3 and E4. So they're in 4 dimensions. It's going to make it a little hard. But each one defines a plane. And I know if I just had E1, E2, and E1 and E3 here, that's easy. I keep E1 fixed and I move E2 into E3. Easy, right? And that made a 3D rotation. Now I've got E1, E2, E3, E4, 2 planes, intersecting the origin of 2 planes inside 4-dimensional space. If I can have a sequence of planes from in between them, from one to the next, that smoothly changes, I can still project the points onto all the planes in between. And that's what's happening here. You see there's a linear combination of both of these axes here. These are the projections of the data on planes in between those, moving through a 4-dimensional space. Okay, so this plane is defined by that and that as the two vectors that are generating that space. Okay? So the only thing that you have to do to watch this is that when we do a rotation, we like to follow, you imagine the globe, right? So you've got this sphere, we like to rotate it along the surface of the globe. So you're following these great circles as points move along. You don't want them going through the center of the Earth, you want them to move along. So that's following, not surprisingly, a geodesic, right? The geo being entirely the Earth. So we're looking at moving along that geodesic. Same thing here, except the notion of a geodesic is the same idea, it's just in a higher dimensional space. You want to be moving along nice short curves through here and moving one plane into the next. So what we're really seeing is a four-dimensional transition. So, whoops, that's when you scroll on the wrong window. We're seeing a movement here through 4 dimensions. But it does mean we can explore this whole space, there's a bug there, this whole space by this wormhole of 2-dimensional plane moving through it all. Okay? Everybody understand what's happening? Anybody understand what's happening? If you do. It's entirely this. I'm moving that thing, that plane through space. It's easy to do in 3D. I could do it through 4D as well. Okay? Okay? That's not a happy face. Okay, you try to get your head around that. You can. Well, I'll tell you what it is. Imagine 3D space, and you're going to do a projection onto just a line. I could take any other line in the 3D space. As long as I move smoothly from one line into the other, I can take lines in between, project the points on it, and you can see how they move, right? And so it's not hard to imagine that happening in 4D space. I can move one line into another anywhere in 4D space, right? Instead of having that line going around a 3D sphere, I've got it going along the surface of a 4D hypersphere. Same thing here. Along this, the ends of these points are along the surface of a 4D hypersphere, just moving along the geodesic along the surface. Okay, and at any point in between, everything you see in the display is a plane, and I've just projected it onto it. Okay, and this gives you some control. You can do far more general things than this by kind of random planes moving around. This gives you control in that you're always moving from one pair of variates to another. So this is very confined. Okay. All right, till next day.